Hello and welcome back. Today we'll tell you about reservoir properties. To understand potential of an oil field, petroleum engineers need to understand, estimate and analyze reservoir properties. Now I'm going to tell you about the major ones. As we already know, rocks capable of containing oil, gas and water which can be extracted during field development are called reservoir rocks. Most reservoir rocks are of sedimentary origin. Once again, there is no such thing as an oil lake. Oil is contained in empty spaces inside the rock, in pores and fractures. Reservoir properties basically describe how good our rock is at storing hydrocarbons and giving them away when needed. The most important reservoir properties are porosity and permeability. By definition, reservoir rocks must contain some wide spaces that can hold fluids. These spaces are called pores. Porosity is the percentage of the volume occupied by pores to the gross volume of the rock. Third, in engineering calculations, porosity is expressed as a decimal fraction. Geologists distinguish between primary and secondary porosity. Primary porosity is pore space that was created as the sediments was deposited. Secondary porosity is pore space that formed after the deposition due to such processes as dissolution, compression, and fracturing. Examples of secondary porosity are caverns that formed after dissolution of lime grains by formation water or due to partial dematerialization of carbonates. It is quite obvious that with depth rock density increases, so the porosity decreases. For practical purposes, we also distinguish other types of porosity. Total porosity is the ratio of the pore volume to the total volume of rock. Open porosity is the volume of pores that are connected to each other. Effective porosity is the volume of pores through which fluid can flow in the reservoir. Porosity depends on the following major factors. Sorting, the better the sorting, the higher the porosity. Packing, the lowest cubic packing gives us a 48% porosity, while the densest hexagonal one only 27%. Grain shape, the more spherical, the higher the porosity. Grain contact, the less contact point, the better. Roundness, the higher, the better. Sedimentary environment and content of shale material, the less shale, the higher the porosity. Sediment cementation, the more cement, the less the porosity. Please note that the porosity value does not tell us anything about grain size, distribution and packing. Rocks with the same porosities may be quite different in physical properties. One more thing we need to understand is the fact that a rock with good porosity will not necessarily be permeable for oil and gas. In other words, not every porous rock can be a reservoir. Besides porosity, it also needs permeability. So that is it. Permeability is a rock property which reflects its capacity to transmit fluids. It determines how well liquids, gases and their mixtures will flow through the formation. The metric unit for permeability is a square meter, and the practical unit used in petroleum industry is Darcy, named after Henry Darcy. It was Henry Darcy who a century and a half ago came up with an empirical equation that is now commonly used in the industry. For this experiment, Darcy used a sand filter through which water was flowing due to gravity forces. Pressure on the inlet and the outlet of this filter can be calculated using H1 and H2 values. This is what Darcy's equation looks like. Permeability is constant if the following conditions are observed. The flow is linear and straight. Chemical reactions between rocks and fluid do not occur. All the pore space is occupied with a single fluid type. The fluid is not compressible. Obviously, this is impossible in real life. We always deal with multi-phase flow, that is, flow of several fluids or phases at once. Each phase flows at its own speed, depending on various factors such as rock properties or phase saturation distribution. Same as porosity, Permeability can be of several types: absolute, effective, and relative. Absolute or physical permeability is raw capacity to transmit a single fluid, measured when the formation is completely saturated with that fluid. It is measured in laboratory conditions using air, gas, or net fluid, because unlike reservoir fluids, these agents will not come in chemical reaction with the rock, altering its properties. Effective permeability is the capacity of rock saturated with water, oil, gas mixture to transmit a particular fluid separately. So this is preferential permeability for one fluid in presence of others. Effective permeability changes constantly during field development. At the early stage of production, when pure oil flows through the pore, effective permeability is the highest and closest to the absolute one. Later, as reservoir pressure is dropping below the critical point, gas that was dissolved in oil starts coming out of the solution, reducing the effective permeability for oil. Then water comes into play, effective permeability for oil gets even lower, which means that more oil will remain in the reservoir, and final recovery factor will be lower. Relative permeability is the ratio of effective permeability of a particular fluid to absolute permeability. Permeability of any rock depends most of all on pore size. The larger the pores, the more permeability. It also greatly depends on the tortuosity of fluid's route. Secondary factors affecting permeability include grain size. The larger the grains, the larger the pores, the higher the permeability. Roundness, the better the higher. Grain shape, the more spherical the higher the permeability. Sorting, the better the higher. Packing, cubic packing gives the highest permeability. Reservoir properties are learned from core analysis, geophysical surveys, and well testing. This is all for now. See you!